right, chapter 14, factorial or two-way ANOVAs. So we've already covered one-way ANOVAs and how to do post hoc comparisons and correct for multiple comparisons. Now we're ready to move on to two-way ANOVAs. So here we're going to have situations where, so this would be like the last chapter, one-way ANOVA. Dr. Petrov is interested in conducting an experiment where we have 30 high school students randomly assigned to a new computer simulation tool for learning geometry, and 30 other students randomly assigned to the standard lecture with paper and pencil problem solving format. So this would be, at this point, a one-way ANOVA. We have two groups, k equals 2. So we have one grouping factor. We're dividing the students up one way into which teaching method that they are assigned to. K equals 2, one grouping variable, one-way ANOVA. That was chapter 12 and 13. But what if, in addition to the teaching method, he was also, or she, was also interested in the effect of sex difference on learning outcomes? What if we wanted to investigate whether the performance or the outcome, the effect of this teaching method depended on the sex of the student? That would be what we call an interaction. So we would have a two-way ANOVA where we would have grouping by teaching method, but also grouping by sex. And instead of saying k equals 2, we're going to use, instead of k groups, we're going to use C and R. C is going to stand for the number of columns or the number of grouping groups, factor levels by the first variable. And R is going to be the number of levels / groups according to the second grouping variable. So instead of just calling groups and grouping variable, we're going to talk about rows and columns. And I think it's important to tell you right off the bat that it does not matter which variable is the row variable and which one is the column variable. The way the computer software knows is it's the order you put them in. The first variable you're going to name is going to be your row variable, and the second one is going to be columns. R is going to be how many levels there are with the first grouping specification, and C is going to be the number for the second. It does not matter. But the way that math works is R comes before C, rows before columns, and that's because of matrix mathematics. That matrices, mathematics, we always state rows before columns. So up here in the corner, I've put, and I'm going to use this color scheme for the whole slideshow here. Orange for rows, green for columns, R by C. So if we were in this situation where we had two teaching methods and say we had 3 sexes, that would be a 2 by 3 ANOVA. But if we had specified the variables in the other order, it would be a 3 by 2. 3 by 2, 2 by 3, it just depends on which order we're specifying the variables. There's no right way to know which one, and the results will be the same either way. It'll just be your interpretation. You'll need to know which is which. So in our analysis of variance, we have already covered one way, and now we're going to do two-way, where we have 2 factors, but you can also go ahead and increase to 3 and 4-way ANOVAs. And the way of the ANOVA, the number of ways, is specifying how many grouping variables you have. And 1-way are common, 2-way are common, 3 are less common, and 4 I have seen very few times. And the reasoning is you need to have, in order to have enough power to affect most reasonable effect sizes, you need to have a good number of participants per combination. And if we have one grouping variable, we have one set of groups, good number in each group. But in this example that we started off with, 3 by 2, there's 3 by 2, 2 by 3, there's 6 different combinations. So we need 6 subsamples. If we go to a 3-way, it compounds the number of subsamples we need. And so the number of sample grows exponentially as you move up in the number of ways. So the number of levels in each factor determines the design. So if we are in this situation where we have a row variable with 2 levels and a column with 3, we'd say it's a 2-way ANOVA with a 2 by 3 for factorial design. But we could have where the row variable had 4 levels and the column variable had 2. That would be a 4 by 2. You can have all combinations. The key here is we have 2 numbers, something by something, because it's a two-way ANOVA. So let's meet the means table. We're going to go with a scenario. Say we have 3 sexes and 2 teaching methods, and I've decided that sex is going to be my row variable and teaching method is going to be my column variable. 3 by 2. This is what my arrangement for my means table would look like. Again, my color scheme. Sex, I'm going to specify a male, female, and other. And just want to put a note here. When we are grouping by variables like this, categorical variables, I said you need a good number, you need smaller subsamples. Often we will make a distinction that even though there might be many sexes or genders, or we are going to collapse into a reduced number because of sparsity and the having to get enough participants in each category. Now, I'm not suggesting that your sex should always be male, female, and other at all. Often we have to do male and female because that's all we have a good enough sample size for. But I wanted to show not a 2 by 2, but a 2 by 3. So that's what I've chosen to do for this illustration. And then we've talked about, that was the very first thing on the first slide, that we have 2 teaching methods, a computer simulation tool and the good old-fashioned lecture, pencil, paper problems. So in this situation, we have 2 columns and 3 rows. But when we specify the ANOVA, this would be a 3 by 2 because the rows come first and then the columns. When we set up the means table like this, we have 6 purple cells. The cells are the combinations, 3 by 2, 6 combinations. And then outside of those cells, those combinations, we have the margins. The margins are when we collapse across rows and collapse across columns, when we average within a strata or a subgroup. And then down here in gray, in the lower right-hand corner, we have the grand mean. This would be the average of everyone in our study. These averages that we're going to put in our cells and our margins, and then this grand mean, these are the averages of our dependent outcome variable. So with an ANOVA, our outcome variable, the dependent variable, has to be continuous, or close enough to treat it as continuous. It also needs to be normally distributed, but we'll get into those assumptions later on. Our independent variables, here we have 2 of them, have to be categorical. And usually we're going to have a few number of categories. If we were doing state and we had 30 states or 52 states, that's not going to work very well with an ANOVA. Usually 2, 3, 4, that's getting quite big. 5, that's a lot of categories. So just keep that in mind if you're thinking of using an ANOVA. And again, the reasoning is all of the combinations, if you think you had 50 states and 4 methods, you multiply those, that's the number of subsamples you need, a good size too. So usually ANOVAs are smaller numbers of groups because of sample size requirements. Okay, now in orange are rows. So we have male, female, and other in this situation. So moving across the rows into the edge of the table, across those purple cells, we get the row means. These are the marginal means for the rows. Now, often you'll see a lot of times these will be denoted 1, 2, 3, which is really bad. It's a lot better if you can label them male, female, other. Here I put a dot. Remember, we do rows and columns. We're collapsing across columns here, so that's why I put the dot. That distinction is that this is for row 1, collapsed across columns. If we all go the other way and we collapse down the columns, now I put the dot first because we're collapsing across the rows and going down in the column. These are the column means, the marginal means for the columns. And then now in the purple cells, these means, these capital M's, and you did X bars and mu's would be the same subscripts. They have two numbers. The first number specifies the row, the second the column. You'll see this notation used a lot, so I wanted to point it out. So these would be in the purple are the cell means. So let's get into the basics now that we know the arrangement of a means table. Factorial two-way ANOVAs. The word factorial means that we have all combinations of our two categorizations of our sample. And we are going to simultaneously, at the same time, evaluate both of the two factors as well as their interaction on the continuous outcome. So we have two factors, and we're looking at what's the effect of teaching method, what's the effect of sex or gender, and we're going to also look at the possible interaction between the two. Now, interaction is a very specific word for an ANOVA. Interaction, and this is a very big word concept for all of statistics, for many kind of models, whether they're ANOVA, regression, and so on. An interaction means the effect of one variable depends on another variable. There is an interplay between the two variables. They could have a dampening effect on one another. They could have an enhancing effect on one another. There's a lot of different ways they can interact. But the idea is that somehow they interplay. Another word that is used a lot in the social sciences for an interaction is the word moderation. We're not talking mediation here. We're talking moderation. The effect of teaching method depends on sex. Sex moderates the effect of the teaching method. That verbiage, whether you say interaction or moderation, means the same thing mathematically. Now, in a mathematical model, an interaction is a combined effect, an interplay between two variables. There's nothing in the math that specifies one is moderating the other because it is a joint interplay. But the word moderation usually has this connotation, this flavor that one is acting upon the other or restricting or having an effect. And I think it's important to point out that in the math that it's a two-way relationship. So, cross-classification. All of our participants can only belong to one of each categorization, one of the combinations of the two factors. They can only belong in one cell. They can only belong to one row specification. They can only belong to one column. So in this one, they only can get one of the teaching methods, and we have to force them into one of the sex categories. Now, this is a hard thing in real life. If we're using observational variables, sometimes we have to force people into categories, and we can't have a bajillion categories, and we can't have small categories. So sometimes we have to collapse, and that's why I chose to do sex with 3 levels, male, female, and other for this example. So when we test a row variable or a column variable, we call that a main effect. And then the interaction effect is when we're looking at, do the effects of these variables interplay, moderate each other? So let's step back and we're going to look at first row, then column, then interaction. If we want to test the row variable to see if it has an effect on our outcome, we want to know, do the row margins differ? And that's collapsing across or averaging across the other variable, in this case, the column variable. So if our row variable is sex, we want to know, are all of the sexes averages the same in the population? Remember, our hypotheses, our null hypotheses, is nothing's going on in the population. And we want to know, is there enough going-ons, differences in our sample data to support the idea that there has to be it's indicative of something going on at the population level. And as when we did some of our other null hypothesis, alternative hypothesis, the alternative hypothesis, we're just going to say something's going on. At least one of the averages is different. So again, for a main effect, we're going to collapse our table in one direction. So if we want to know, does this row variable have a main effect, we're going to collapse across and look at just the margins at the edges of the rows. If we want to know about the column effect, does the column variable, breaking up in columns here, teaching by the old method, teaching by the new method, does that have an effect? We're going to collapse down through the sexes and say, do the columns have different averages? Do those population averages, are they the same or different? So we would collapse down. Now, the trickier one, an interaction effect. An interaction effect means there's some pattern that is not the same throughout the table. So the differences across rows are not the same. The patterns in the rows are not all the same. The patterns in the columns are not all the same. There is something else going on. A lot of times, instead of looking at the tables and looking at the cells in rows compared to the cells in columns, it's a lot easier to do this investigation with a plot. So I've shown you kind of the means plots, first rows, columns, and then interaction. But it's important to point out that when we do the investigation with a two-way ANOVA, we always want to look at and to evaluate the interaction first. When we do a two-way ANOVA, there's multiple possible outcomes, and you're always going to want to look for this one first. Is there a significant interaction? Always first, look at the interaction. See if it's significant. And that's, if there is an interaction, that's what we need to talk about. Those are the results we need to present. That's what we need to probe the interaction or do a interaction contrast, which we will talk about more. That's the first thing you need to look at when you run a two-way ANOVA. If there is an interaction, be extremely careful about interpreting main effects, because remember, a main effect collapses across the other variable. But an interaction says the effect of a variable depends on the other. And so if there's an interaction, you should not be collapsing across the other variable and looking at main effects. And this is something that as a statistician I see done incorrectly a lot of times. If there isn't a significant interaction, if you look at that interaction first off, it's not significant, then you can look at the main effects. And you might have both of the main effects being significant. You might have just the row or just the column. Or in another situation, sometimes we have no significance for any of our variables, not the interaction, neither the main effects. So those are the main outcomes that you can have with a two-way ANOVA model. Either we have a significant interaction, that's what you need to focus on. If there's no interaction, then you can step back and look at the main effects one at a time. Problems with ignoring factorial design. If you treat each cell as a separate group and run one-way ANOVAs, collapsing across, that can help you establish main effects in a cumbersome way that's less powerful. But the bad thing is it, besides the loss of power, it doesn't let you investigate possible patterns, i.e. interactions, which are often more important, interesting, and what our hypotheses are about in real life. So whenever we gather data, why do we not have one participant? Why don't we have two participants? Why do we want a lot of participants? Well, because people are not all the same, and we want to control for person-to-person variability. People are different. There is just noise and error, and we want to control for that. By getting a big enough sample, we can kind of tease apart person-to-person variability. The more we can reduce person-to-person variability, the higher our power can be. And that's why larger samples have more power. Another way to reduce the within person or the within group or within cell variability is by adding additional factors to our model, as long as those factors explain subject to subject variability. So in our initial example here, we wanted to know, does the new teaching or the old teaching method have an effect? Does the teaching method have an effect. Well, is it reasonable to think that the effectiveness of the teaching method depends on the sex of the person? Maybe one is preferred by another. Maybe for one sex or gender or ethnicity or you name it, it makes a bigger difference, and some it doesn't. If we can capture that thing that makes a difference and divide our sample up, we end up with smaller cells that are more homogeneous. Homogeny is a good thing for models in terms of our cells. The more homogeneous our cells, the lower our subject-to-subject variability within cell, then the more power we have to investigate other effects. Now, it's not always possible to do this, and there's a downside. If we put a factor in our model, say we did hair color, is it likely that hair color has something to do with or an interplay with teaching method? I'm going to say being blonde does not have a geometry effect on which teaching method is better. In that case, if we add a factor to a model that does not have an effect, we don't increase our power, and actually it can be slightly harmful. It can slightly decrease our power by changing our degrees of freedom. So there are some alternatives. If we cannot come up with a variable to divide our sample by, say sex, and we don't want to just willy-nilly choose something, hair color, eye color, shoe size, that has nothing to do with it. Other alternatives are doing a repeated measures design, if it's applicable in your situation, in your research area, because in that way, each person serves as their own control, and we have some more homogeny there. But we'll get into more of those options in the later chapters. We have a few more to go. So I kind of brought up assumptions to begin with. Similar to a one-way ANOVA, we have very similar assumptions. One is that our observations are all independent of each other. The second is that our outcome, our dependent variable, is normally distributed, but instead of being normally distributed within each group or overall, it needs to be normally distributed within each subgroup, as in each cell, each combination of grouping variables. And then the third one is that we need to have a homogeny of variance. So each population, each cell needs to have about the same amount of variance. We want that variance to be as small as possible, but we want it to be similar across all the different combinations of our grouping variables. So just like one-way ANOVA, there's no way to fix a lack of independence. So we want to make sure that we plan well, because you can't test for lack of independence and you can't fix lack of independence. So when you gather your sample, you don't want to have a cluster sample if you're going to use an ANOVA method. Now, if you have a cluster sample, as in you have students that are members of classes with the same teacher and then they belong to different schools, there are ways to handle that with multi-level modeling, and that's a really powerful tool, but not with one-way ANOVA, not with two-way ANOVA. To check for normality in our outcome, our dependent variable, the best way, we've talked about this a lot of times, is with a plot, like a histogram, a QQ plot, box plots. And remember here, we don't just want normality in the outcome variable at large, we want normality within each of the subpopulations in the combinations of our factors. And the same thing goes for homogeny of variance. We're going to run Levene's test to look for homogeny of variance, but now we have not just one grouping variable, but two. And we want all the combinations of those two grouping variables to have homogeny of variance. Okay, so let's get into actually running the ANOVA. When we run the ANOVA, we're going to run this as f-tests, just like we did in a one-way ANOVA. In the one-way ANOVA, we built an ANOVA table where we had a grouping variable, and then we had within group variance and total variance. And we had some columns. Now the first column was summa squared. The summa squared within group and between groups, that adds up to the total. Degrees of freedom, between groups, within groups, that adds up to the total. So these first two, summa squared and degrees of freedom, have 3 cells going down. For between groups and within groups adds up to the total. But when we move over to the mean square, summa squared, there is no third box. It's just the pink and the blue in this one because they don't add up. We get the mean squared value by taking the summa squared value and dividing by degrees of freedom. And then we make our F statistic by dividing our mean squared between groups by our mean squared within groups, gives us an F value, look up the P value by using the degrees of freedom. All of that is going to be replicated in a two-way ANOVA. Yay! The difference here is instead of having one grouping variable, we have two, and we're going to denote them rows and columns as well as their interaction. So now instead of having just one F test, we're going to come up with three F tests. Instead of having one P value, we're going to have three P values because we have the two main effects and the interaction. A two-way ANOVA has three effects. Both of these one-way and two-way ANOVA have within sum of squares, within degrees of freedom, within mean sum of squareds, the within. But in a one-way ANOVA is within groups, and with a two-way we call it within cell. So that's a little bit different. So let's start off with our first column, our sum of squareds. In the one-way ANOVA, we had three sum of squared. In a two-way ANOVA, we have rows, columns, interaction within, and total. So we have lots of sum of squareds here. So let's look at them. So partitioning the variance. We said that there's a person-to-person variation, observation-to-observation variation. And we're going to focus on the situation where we have balance, where we have the same cell size across all of our combinations. So in the one-way ANOVA, we took our total variation and we partitioned or divided it up into two pots, the between groups and the within groups variation for our K number of groups. Now when we have a two-way ANOVA, instead of just dividing into K groups, we have rows, main effect, columns, main effect, and the interaction. Remember, we're going to have three tests, three F tests, three P values. So when we divide up or partition our variance, we have those three piles for our two main effects and our interaction, and then with our within cell. We still have a total, we still have within, but we have three effects instead of one effect. Now, the next few slides, there are a lot of formulas, and you don't need to memorize these, but I wanted to point out some things here. To do the sum of squared for the rows, if we look at these formulas, there's two different ones. The top one is the one we usually use if we're doing it by hand. The bottom one is the one that the computer likes better because of the way computers work and their funny minds. Both of these formulas, well, it's top formula specific, we'll focus on that, uses in here the row means, the row sizes, and the grand mean. If we move to the columns, formulas look very, very similar. Here we have column means, column total sample sizes, and grand mean. So again, we have the two versions, the person, paper, pencil preferred method, and the bottom one, which is the computer preferred method. And then, so we have the row variable, which is looking at the row means collapsing across columns. The column variable, looking at the column means collapsing across row. And then we have the interaction. And again, I'm not going to look at these formulas too heavy, but now we're looking at the cell means with the cell sample sizes and the grand mean. But what we are doing here is we're looking at the variability among cells after removing or after partitioning, after controlling for the main effects of row and column. And we do that by subtracting the sum of squared for rows and columns out of this formulation. I don't think you have to do any of these by hand. I hope not on the homework. You definitely won't on the test because gag me. And then the sum of squared within. Here we have three different formulas that do basically the same thing. I just want to focus on the last one down here. Usually if we have to do this by hand, we're usually, which I think this is the one that we fall into on the homework, usually to find the sum of squared within, we take the sum of squared total and subtract the other components because we know they have to add up. Okay, so the sum of squared, there's the nastiest to do, but there are those formulas, and as long as we have only two rows or two or three rows and two or three columns, it's not too much of a headache. I think there is one on your homework. Let's move to degrees of freedom. These are a little bit better. Degrees of freedom in the two-way ANOVA. So here I have the specification of degrees of freedom for a one-way ANOVA to remind ourselves. We said in a one-way ANOVA, we had K groups. Degrees of freedom between groups is number of groups, subtract 1. And within groups, total sample size minus K. It's going to look pretty similar, but instead of having K number of groups, remember we're grouping our subjects two ways. So we have rows and we have columns. R being the number of rows, how many ways we're breaking up that row variable, and C equal to the number of columns, how many different groups there are for that column variable. NT is still our total sample size, the total number of observation. Little n, instead of being number of observations per group, is number of observations per cell, combined groups. So if we remind ourselves, degree of freedom tree here, we said we're going to take the total and divide it up. In the one-way ANOVA, we did one division. In the two-way ANOVA, instead of just dividing between groups and within groups, we've got three effects. And so when we divide it up, first we're going to specify between cells and within cells. And the formulas might look a little familiar. So between cells, how many cells do we have? We have three rows, 2 columns, that's 6 cells. Instead of being K minus 1, it's number of cells minus 1. Instead of being total sample size minus K, it's total sample size minus number of cells. And then the cells, we have cells are specified by their row and their column and the interaction. So the degrees of freedom for the rows is the number of rows minus 1. The degrees of freedom for the column variable is the number of columns minus 1. And the interaction means multiply. We're going to multiply the degrees of freedom for rows and columns together. For this, I have a second YouTube video, which is uploading right now, that has a walkthrough of the specific example with the sleep and stimulus on the motor driving task that Barry Cohen presents in our textbook. So it'll actually put some numbers in there. So we have sum of squared with those yummy formulas, degrees of freedom, we're doing our splitting trees. Now we're on to mean sum of squared. These are our variance estimates. The formula for all of our mean squared are the same way we had in the one-way ANOVA. We take sum of squared divided by degrees of freedom. But we have more than one of these. We have mean squared for row, mean squared for column, mean squared for the interaction, and our mean squared error. Now that mean squared error is sometimes called mean squared within cell, mean squared W, mean squared error, mean squared residual, or just MMSE. All of those phrases, words, abbreviations, denotions all mean the within cell variation. Now, this is not sensitive to either of our factors or their interaction. This is purely person to person, observation to observation, noise, residual variation. Okay, now, once we have that, we can build our 3F statistics. This can be called an F statistic, an F test, or an F ratio. Ratio because we make a fraction to calculate the number for F, our F statistic, that we use to test and get the p-value. Every one of our F ratios, F tests, are built the same way. They always have a mean squared for the thing we want to test. That could be different. That could be row, column, or interaction. And then we're always going to divide by the mean squared error, mean squared within cell, mean squared W. So we're going to get 3 different F statistics and 3 different p-values, 2 main effects, and the interaction. So we'll get an F statistic for the row, F statistic for the column, and F statistic for the interaction. Now, rows, columns, and interaction will always have a different formula for the numerator degrees of freedom. Now, if you had 2 rows and 2 columns, you're going to have 1 degree of freedom for each row and columns. They would be the same in that case. If we have 3 rows and 2 columns, we're going to have 2 degrees of freedom for one test, 1 degree of freedom, at least for the numerator, for the other one. So the numerator degrees of freedom is probably going to be different for each F test, possibly. But the denominator, the number on the bottom of the F ratio, and the denominator degrees of freedom will be the same for all three of our F tests. So we need to be careful. When you're doing an ANOVA by hand, which you have to do once or twice on the homework, when you calculate your F ratios, your F statistics, when you are trying to look up in the table to decide if it's statistically significant, pay attention to the degrees of freedom, because you might have to look up a different critical value for each one of the three tests, for each of the main effects and their interaction. But the denominator number on the F test and the denominator degrees of freedom will always be the same for all three F tests. So here is a copy of the formula sheet that I put together for the class. I've tried to put all of those formulas we just went over for sum squared, degrees of freedom, mean sum squared, F, all of it in one place. Plus we've got the effect sizes down here, which we haven't talked about yet. So this is something handy to keep in your notebook for future reference and for the test possibly, so you can use that and not have to memorize all of these messy formulas. Okay. So we said down here on this formula sheet, down here, there's some effect sizes. So let's talk effect sizes now. So the F test says, is there any statistical evidence that there is an effect? And we always want to follow that up with, how big is the effect? Is this something that we should be concerned with, or does it have little to no practical importance? So if there's an effect, how big is it? When we did one-way ANOVA, we calculated an eta squared. Eta squared tells us the proportion, kind of like a percentage, proportion of variance in the outcome accounted for by a particular factor, or the interaction in this case. So we can have three effects. Remember, the main effect of the row variable, the main effect of the column variable, and the interaction between those two. So each of those three effects can have their own eta squared. To do the eta squareds, you take, for whichever effect you're doing, you take its effect, sum squared, and divide by the total sum squared. That gives you what we call an ordinary eta squared. One-way ANOVA, we did the SS between divided by SS total. In a two-way ANOVA, you would take, for the row variable, the column, or the interaction, whichever one you're doing, their own sum squared divided by the total sum squared. And just like the one-way, we have some ranges to be considered small, medium, and large. And you all know how much I just love these ranges. But in general, if a partial eta squared is between 1 and 6% of the variation, that's usually considered small. Between 6 and 14, considered large. Over 14%, considered pretty big. Now, with these ordinary eta squareds, they work really well for a one-way ANOVA, but a two-way, they are sometimes lacking. And so they're just like we have an omega squared for a one-way ANOVA, we have omega squareds for two-way ANOVA. And here we go, I'm throwing you out a formula. You interpret it the same way as an eta squared, but omega squared is not as biased. This is what we should be using, but nobody really does. Why? Because formula is not as straightforward, and software hasn't spit it out by default in the past, although that's changing. A bigger thing that people usually do that they should be doing is, instead of an ordinary eta squared with a two-way or higher ANOVA, is doing a partial eta squared. And you can know that it's a partial eta squared because it's the eta symbol with the two superscript, but with a p subscript. And there has been some confusion on this in the past because earlier versions of SPSS gave partial eta squared, but they didn't denote the fact that it was a partial eta squared. It just said eta squared, even though it was a partial. So that led to all confusion for like 5 or 10 years. Anyway, when all of your factors, your grouping variables, are experimental, or when your factors are, you have more than 2 factors in your analysis, what happens is the sum squared for the factors in interaction tend to be really small because we're slicing and dicing a lot of ways. And so instead of having the sum squared for the effect divided by the total sum squared, we divide by a smaller quantity. This is where the word partial comes from. Instead of dividing by the sum squared total, we're going to divide by the sum squared of that effect, the top number, plus the sum squared within, that residual error. And this gives a more proportion of variance accounted for a particular effect in a partial world. And this is what is by and large reported correctly for two-way ANOVA is partial eta squared. And you should use these. There is a partial omega squared, and its formula is just so yucky. Nobody uses this, but they should. Okay, so the strength of a two-way ANOVA. Two-way ANOVA's strengths lie in their ability to assess for and to evaluate possible interactions between factors. This idea of moderating effects. This is the bonus. This is the good thing about a two-way ANOVA. So the interaction between two-way factors is called a two-way interaction. If you have a three-way ANOVA, an interaction between three factors is called a three-way interaction. Yeah. Three-way interactions are rarer. A lot of people say to be very skeptical of them, but I will tell you, I have been a part of research that has found and published statistically significant three-way interactions. So they do happen and they are significant, but you want to be careful. A lot of times they're hard to find because of power. People are more often skeptical because of the difficulty in interpretation, but if you can make plots, you can interpret. So we can do it now. When we have an effect, be it a main effect or an interaction, if it's statistically significant, that's telling us in an interaction that the effect of a factor is not the same for all levels of a different factor. There is some interplay or dependence on the effects between the two factors. The effect of this variable combined with the effect of that variable is different than what you would think of them separately. For instance, if I have a teaching method, and if you do this new teaching method, you can expect your score to go up by 10%. And if you get enough sleep, you can expect your score to go up by 20%. If you do both of them, is it going to go up by the added 10 and 30%? Or is it going to go up by more or less? That's the idea of an interaction, that the combined effect is not just the sum of the separate effects. These are the most interesting and the most sought after result, the hypotheses we most often want to investigate, but they can be harder to deal with. The whole key here is to make a plot. And so let's look at some plots. When we plot our interactions, there are two main plots that can kind of come out of it, assuming we do have an interaction. The first we call ordinal, the second we call disordinal. Ordinal means the direction of the effects is similar for the subgroups. Disordinal means it's reversed for some groups. So here I'll give you an example. So here is left hemisphere and right hemisphere strokes for male and female. And we have phonemic errors, the mean number of errors people make. So if we look at this plot, are the lines parallel? Nope, one's more slanted than the other. If we look at the gaps for left and the gap for right, for left hemisphere, there's a bigger gap between male and female, and the right hemisphere, there's a smaller gap between male and female. The gaps are different sizes. However, in both left and right hemisphere, the male participants are making more errors than the females. This is an ordinal effect because the order of male and female is the same for left and right hemisphere. Here we see gaps of different sizes, but the ordering of those gaps is the same. This is the only situation where having an interaction, you could look at the main effects and interpret the main effects. Because when you collapse across hemisphere, you will see an effect of gender, and collapsing across gender, you'll see an effect of hemisphere. But if you do that and only look at the main effects, you will be masking this interaction, this gap wider and narrower thing that's going on. The second plot I'm throwing up now, disordinal. Disordinal, not only are they not parallel, but they are actually crossing. If we look at the control group, the high SES, the blue diamond, is higher, has a higher test score than the low SES. But if we look in the treatment group, not only is the gap a different size, but we see a reverse ordering. In the control group, high SES scored higher, but in the treatment group, low SES scored higher. It's not just a reduction in the gap, it's a reversing of the order. When we see crossing, that when we do our means plot, that's disordinal. In a disordinal interaction, you will never want to look at the main effects. So plot your data to know whether you should look at main effects. So interactions, I think I beat this horse a few times today already. If you are doing a two-way ANOVA, always look at that interaction term first. If it's significant, interpret it, not the main effect. If the interaction's not significant, well then, by all means, look at the main effects. Tempering or contingency of effects, that is an interaction that can mask or make the main effects look non-significant when the factors really are significant. And this is the thing that probably causes the most confusion in two-way interactions. So again, plot your data, plot your means, look at your plots. When you make your plots, you always want your continuous dependent variable to be on the y-axis. Your x-axis, you want to put one of your factors. Usually, of our two factors, row factor and column factor, you will want the x-axis to be the factor that has the larger number of levels. Are there more rows or more columns? Or the ones that have the most order to them. So if one of your factors goes on the x-axis, what do you do with your other factor? If you put row groups on your x-axis, what do you do with your column groups? You have some choices. Different shapes, different colors, different lines, different panels. We'll be doing these in the homework so we can get that down. The book, this is a figure from the book, has made some of these and so delightfully called them factor A with levels 1 and 2 and factor B with levels 1 and 2. Same way on your homework. I'm sorry I didn't make it up. So this first plot does not have an interaction. How do I know that? When I look at the plot, when I have my 4 means, this is a 2x2 ANOVA. Our factor A has 2 levels, factor B has 2 levels. So ingenious. We have parallel lines, if not identical lines. If they're parallel, there's no interaction. Now, those lines can be really, really close together. They can have a gap between them. The key with there being no interaction is that the gap is consistent. Now, here's a third example. We have not flat lines, but diagonal lines. But notice the gap. The gap between the line is constant. The lines are parallel. No interaction means parallel. They can be close together, far apart, flat, diagonal, one way or the other, as long as they are consistently the same distance apart. They're parallel, no interaction. So no interaction can look different ways. Now, this one. I'm going to throw up 4 more plots. All of these next set of plots have an interaction. So we're going to see lines that are not parallel. And there's more than one way for lines to not be parallel. This first one is the classic way people think of an interaction. Our lines are crossing in a full-blown X. If you see lines on your means plots that are an X, that is an interaction. The second plot, these lines are not crossing in our plot, but they would if we extended our lines. They are not parallel. Above the letter A1, we have a small gap. Above the letter A2, we have a large gap. The gap is different sizes, so the lines are not parallel. This top plot with the X, this is a disordinal interaction. The second one is an ordinal interaction, but both of them are interactions. Now, crossing lines can be in a perfect X, they can be in a slanted X. Doesn't matter, still an interaction. And the last one, again, we have difference in gaps. Now, in all of these plots, they're organized by yes or no having an interaction. But it also goes on to specify whether the main effects are significant or not. And I urge you to look at those figures. So, when is the only time we would interpret main effects? In the presence of an interaction? Well, we can look at main effects if there's no interaction, but if there's an interaction, we can cautiously look at main effects if it is a mild interaction, as in the effect size is small. How small? 0.3, 0.4, 0.03, 0.04 for partial eta squared, and it's ordinal. This slide is key. There's a high chance that you will have to refer back to this slide at some point in your career, either in reading something or having a mentor or a co-author or a reviewer that would come back here. I've given you a citation. Please, if you have an interaction, be very, very, very cautious of ever looking at those main effects. Okay, if you have an interaction, results can be distorted if additional factors are included in the analysis and not tested. So here's an example. We have an experiment where we're looking at a drug. Maybe this drug has an opposite effect in men versus women. What happens if we have a sample and we didn't keep track of or investigate gender or sex? It might look like the drug does nothing, when in fact the effect depends on the gender of the person. Gender moderates the drug's effect. So when we're looking at proposing or designing a study, this is where you experts in the area have to think about what are potential moderators that we might need to include in our analysis. It's not good enough to just say, does a drug have an effect? But does it have a constant effect or the same effect among genders, among ethnic groups, history, all other conditions? If interaction terms are non-significant, that can increase our confidence or our generalizability. So even if we don't expect there to be a moderation, you might want to collect data and run a test to prove no interaction to show that the treatment effect is the same across sexes, or a teaching method or a therapy has the same effect across ethnic groups or across family histories. So our ANOVA is an F test, or in this case, a set of 3 F tests, 2 main effects and an interaction. The ANOVA analysis tells us omnibus, overall, if we have an interaction, and if not, if we have main effects. Anytime we have a significant p-value on any of those F tests, we have to follow them up to see where the effect is. The only time we don't have to do this is a 2x2 analysis. 2 rows, 2 columns. So, follow it up. Factorial ANOVAs overall. We need to know what groups are different. And just like in one-way ANOVA, if we follow it up with multiple tests, we have to control for multiple comparisons. And the type of results, are we looking at the interaction? Are we looking at the main effects only? That tells us which kind of test we're going to do. So for each of the 3 F tests, we can do planned comparisons. And if we do a planned comparison, we don't need to do a multiple comparisons adjustment. Or we could do an post hoc test where we would need to. Now, when you're doing those 3 F tests, you don't need to do multiple corrections for the 3 F tests. Just for the probing of the interaction, looking at simple main effects. So anytime we have a factor with only 2 levels, we don't need to do multiple comparisons if we're just looking at the main effect for 2 levels. If we have more than 2 levels and we want to look at 2 of the 4 levels or 2 of the 3 levels, we can do the pairwise t-tests and use Tukey's if we have Tukey's HSD if we have 4 or more groups, and it's getting late. Fisher's LSD if we had 3 or less. Bonferronis is always an option, but I would try to avoid it whenever possible. If we're going to do a complex contrast, whether it's a linear contrast or a interaction contrast, which we're going to find out about in the example, then you need to look at using Chaffee's or even Bonferroni's correction in those cases. So another way that you can follow up interactions is to do what we call a modified one-way ANOVA of a simple main effect, and those are usually done by hand, and it's by hand but using the results that we get from the overall F test. So the two-way ANOVA provides us the mean squared within, and then we can find the mean squared between by doing a one-way ANOVA. I'll get you an example of that so we can look at it together. Interaction contrasts are probably the most frequent follow-up test to a two-way ANOVA. When you have an interaction that's significant in a two-way ANOVA, following it up with an interaction contrast is a good way to show where things are significant. Just not that there is a difference, but where the difference is. If we have a 2x2 design, those get really simple. If we have a 2x3, there's 3 possible ways to do those interaction contrasts. So often we have to pick which ones we're going to do. And again, I think it would be best if we looked at the example on that one. Okay, so set that aside for a second, looking at interactions. If, when we do our two-way ANOVA, and first we look at the interaction, it's not significant, then we turn our attention to the main effects. And main effects, we look at the F value to see if there's anything going on for either one of the main effects. And if the answer is yes, the main effect is significant. If there's 2 levels to that factor, you don't need to do any multiple comparisons. You can just say they're different. If we only have male and female and it's a main effect, we know it has to be males and females that are different than each other. And we can look at the marginal means or the means plot to say which one's higher and which one's lower. If we have more than 2 factor levels, then we do need to follow it up with either a one-way or some contrast statements. We can do simple or pairwise or complex, and we will work these out together on the examples on the homework and office hours I'll be recording tomorrow, and as well as the textbook example. And so here's just a picture of that. So how do we write our results up APA style? Well, same things apply that we've talked about with one-way ANOVA. You want to give some background. Usually in the method section, you've already said who your participants are, what are your variables, which one's your dependent variable, what are your grouping variables. Thing is, here we've got 2 grouping variables. So you could say, we are going to compare the, what's our example here? Oh, the math scores at the end of the chapter between groups that use the traditional versus the new method, between males and females. So we have our dependent variable is our continuous math score. Our 2 factors are the 3-level sex variable and the 2-level teaching method variable. It's often then we're going to say we're going to do descriptives. The means table is very, very helpful in reporting, either as a table or as a plot. I said this before, you don't need to report the mean squared within, although historically people have. You do need to report all 3 F statistics. Even though we might not interpret the main effects, you will want to report the F values with their degrees of freedom and P values and potentially effect sizes for both main effects in the interaction, as well as any post hoc or planned comparisons you follow them up with. Cannot stress this enough with two-way ANOVAs. Anytime you have interactions, you want a figure. You want a figure, you want a figure, you want a figure. So conclusions. Non-significant interaction, follow up the main effects. If you have a significant interaction, you've got to probe that with post hoc tests, and that's what you want to interpret and focus on. Okay, side note, just in closing, imbalance. ANOVA methods were developed in agriculture by Ronald Fisher. Dealing with plants, very controlled, very easy to balance, very easy to randomize. They would genetically engineer seeds, they would control the light, the soil, the temperature, the water, very little dropout, human subjects. Hard to do all of that. Hard to get all of your cell or your subsample sizes all equal because of attrition, and we can't randomize a lot of things that are factors, like gender or sex or family history or medical condition. These are not randomizable factors. And so often it's hard to recruit in some groups. We might end up with cells that are different subsample sizes. In those cases, ANOVA methods are not your go-to method because the results are not always going to be valid and they're not reliable. If you have data, whether you planned it or not, that you get unbalanced design or you have unequal cell sizes, you need to be very, very careful. It's not your fault. It's just the nature of the beast of human subject design. The problem is that your sum of squared between cells will not always equal when you add up the sum of squared for rows, for columns in the interaction. And so there you have this lack of independence between your factors. So all of the previous equations we've talked about, any R commands that I give you, you can run them on unbalanced data. It usually will not stop you from running it, but the p-values will not necessarily be valid. These bubble charts are sometimes showed, they're not my favorite, to show that you get overlapping of factors with unbalanced data. If your imbalance has happened due to randomness, meaning just you had maybe one or two random dropouts, it's not so much a concern. The validity of your ANOVA is probably still okay. Otherwise, if you do have imbalance or unequal sample sizes, you need to do something with your ANOVA, not just take it the default. Some of these things are doing weighted means. People have tried that in the past. It doesn't really work very well. Harmonic means of sample sizes are used to do weighting. But again, time has told us that this has not been a very good approach. There are alternative sum of squared calculations that handle the non-overlapping. They call them type 2. Usually we're going to use type 3 sum of squared. That's the default in SAS, SPSS, and R. But you can do, and these numbering are awful, and they were based on the SAS manual from years and years ago. They call them type 2 and type 4 and type 5. They're out there and you can do them, but really, if you have unequal group sizes, the better way to handle that is with a regression, not an ANOVA method. And that could be single level regression, which is the follow-up to this class 7610, or multi-level modeling, mixed effects modeling, which is a class I teach every fall called Psych 7650. So that can handle social science, the regression approaches, a lot better than ANOVA. And it's that reason that the 6600 class, it's a love-hate relationship with me. I love that we get to talk about interactions because that is so crucial to social and psychology and educational research, the idea of moderation in interactions. But using an ANOVA only method really limits you. But this is our foundation so that we can move forward and do the regression classes and those methods. So just to kind of give you a background, I told you type 3 sum of squares are what we use for our ANOVA methods, and most regressions use those. And then there's the type 2, which are partial sequential, and type 1, which are sequential or hierarchical sum of squared. You have the option in our R code to do a type 2 or a type 1. There is also a 4, 5, and 6. They generally are not good choices commonly. If you have unbalanced data, I'm not going to go into a lot of this in this course. I would urge you to talk with a statistician or someone with more expertise or do some reading. If you're still here at Utah State, I'm your gal. Come talk to me and we can figure out what's the best approach. For balanced data, most of those type 1, 2, 3 sum squared get the exact same results, so you don't need to be concerned with that. So that's the end of this recording. And again, takeaway, always look for that interaction first. Plot your data, plot your data, plot your data. That can help you understand. Look at the F tests first, follow them up with contrast, pairwise contrast statements, pairwise t-tests, and reduced smaller one-way ANOVAs. So we'll see you tomorrow, hopefully during the office hours, and I'll get that recording up too as soon as possible.